Hi, I'm here to talk to you about the Heisenberg Uncertainty Principle. What does it mean? How does it affect our calculations in quantum chemistry? We use light in order to measure the position of electrons, and the uncertainty of our electron's position can be related to the wavelength of light used. A larger wavelength of light would result in more uncertainty in position. But now one would ask, well then why don't we just use a smaller wavelength of light in order to minimize uncertainty in position? Light has energy, and the smaller the wavelength of light, the higher its frequency. And we know from the photoelectric effect that the higher frequency light imparts more energy. When this energy is imparted on the electron is excited. It starts moving faster as a result, so now the uncertainty in its momentum has grown. So due to the nature of light and how it interacts with electrons, the uncertainty of an electron's position and momentum are inversely related to one another. As one increases, the other decreases. So now some of you are probably thinking, all right, great. Today I learned that light really sucks at measuring stuff from an electron. If we develop technology advanced enough to measure position from an electron that didn't involve using light and disrupting it, could we go around the uncertainty principle entirely? The answer is no. The Heisenberg Uncertainty Principle describes a fundamental property of quantum systems and isn't a statement about the limitation of technology. The uncertainty principle is inherent in all wave-like systems and comes up in quantum mechanics because everything on that small of a scale has wave-like properties. It was Werner Heisenberg in the 1920s that performed a series of experiments that concluded that for any particle, the uncertainty in position multiplied by the uncertainty in momentum had to be greater than or equal to Planck's constant over 4 pi. Fortunately for those of us living in the macroscopic world, h bar over 2 has an absolutely minuscule value of 5.27 times 10 to the negative 35 joule seconds. A much larger value, and you probably get to say fun things like, I'm around 20 meters from the library, plus or minus 4 feet with how vigorously I'm vibrating in every direction. But thankfully, due to our comparatively massive size to the quantum world, our positions and momentums are much, much greater than h bar over 2, to the point where this concept doesn't really affect our daily lives at all, outside of studying quantum mechanics.
To understand how the Heisenberg Uncertainty Principle works formulaically, we consider the following. The behavior of the electron is restricted to a region. It possesses both wave-like and particle-like properties, that is, it has mass and velocity. The position of the electron cannot be exactly determined, but only within a range of accuracy delta x at a given time. The velocity of the electron corresponds to a wave-like disturbance, which constantly changes its size and shape and therefore cannot be defined exactly. We define momentum as a product of the electron mass times the velocity of the electron. But because we have these wave-like interferences, also known as wave packets according to Heisenberg, we get that there's a difference in momentum for this particular electron. So we now consider the wave properties of this velocity. So we take the velocity of the wave packet to be the Planck constant divided by the mass of the electron and the wavelength of that wave, and then we count the difference of the wave packet by this equation right here. Planck's constant divided by the mass of the electron times the initial wavelength squared times the difference between the two wavelengths. We get the difference in momentum to be the mass of the electron times the difference in velocity of the wave packet, which pretty much comes down to the mass of the electron times the difference of the velocity to be synonymous with the difference in momentum that we described in the previous column right here. Putting all this together gives you the Heisenberg Uncertainty Principle above, where delta x times delta p is less than or equal to the Planck constant, where the Planck constant is 6.6 26 times 10 to the negative 34th joules times seconds.
One application of the Heisenberg Uncertainty Principle is that it can explain quantum tunneling. Quantum tunneling is the phenomenon in which a particle can pass through a barrier even if it does not have the required energy to pass through it. For example, say we have a particle in a box with a box of length x with the energy of E inside of the box and a potential energy of V everywhere outside of the box. We will assume that E is less than V and that the particle is trapped inside the box. As we get closer to measuring the exact position of where the particle is in the box, the greater the uncertainty of the momentum for the particle is, which is described in the Uncertainty Principle equation. Using a relationship between energy and momentum, right here, where energy is equal to the momentum squared over the 2 times the mass, we see that if we increase the momentum, the energy also increases. Due to this relationship, it is possible for the uncertainty of the momentum to be large enough that it gives energy of the particle to be greater than the potential of the barrier, allowing the particle to be outside of the box. In classical mechanics, if a particle had energy less than the potential energy of the barrier, there would be no probability of finding the particle outside of the box. It is because the size of the particle, they have wave-like properties and follow a quantum mechanic phenomenon known as quantum tunneling, giving them a probability to be on the other side of the barrier even though initially the energy is less than the potential energy. Heisenberg's uncertainty principle proves this to be true due to the uncertainty of the momentum, allowing energy of the particle to have a probability of having energy greater than the potential energy of the barrier that it is in.